So in 153, we just talked about exponential equations. So I'm going to do an example here. Y equals 2 to the x. And I said, in class, I said, can you graph that? And a lot of people hesitated. And so I said, well, let's just make a little table here. Figure out some x values and figure out what the y would be. So if x was 0 or 1 or 2 or 3 or -1 or -2, what would this be? Now you can type them into your calculator and you can see these values, but let's just figure out. 2 to the 1. That one people usually get right. That's 2. And 2 to the second, 2 squared is 4, and 2 to the third is 8. 0, some people struggle with. -1, 2 to the -1. Well, minus on a power means it belongs in the denominator, so it would be 1 over 2 to the 1, which is 1/2. So 2 to the -1 is 1/2. And 2 to the -2 means 1 over 2 to the +2, which is 1 over 4. So the minus just means move it down to the denominator and then square it. Or move it to the denominator and take it to the 1 power. So what does it mean to be 2 to the 0? Now to explain that, I said, well, what do you do if you had like x to the 4th divided by x to the 3rd? That means there's 4 x's multiplied in the numerator and 3 in the denominator. 3 of them cancel 3 of them, and that would leave just x to the 1, or just x. And you get that by 3 from 4 is 1. So you subtract the exponents. So what would you get if you did x to the 3rd over x to the 4th? Well, 4 from 3, you'd get x to the -1, which is, if you think of it the other way, 3 x's cancel 3 of them and leaves 1 over x. So you can see x to the -1 is 1 over x, like I did here. So how would I get 0? Well, that would be x to the 3rd, say, over x to the 3rd. And 3 from 3 is 0. Just using the subtract the powers. But x to the 3rd is the same as x to the 3rd. And when you have something over itself, like 2 over 2, that's 1. So something to the 0 power means we're dividing the same number of them in the numerator as the denominator, and it makes a 1. Now, did it matter what x was? No, not really. So anything to the 0 power is 1, except maybe 0, because you can't divide by 0. So that would be up to a question, 0 to the 0. That's a later mathematical question. But right now, anything to the 0, for the most part, if it's not 0, we'll call it 1. So what's the graph of 2 to the x look like? Well, 2 to the 0, 1. 2 to the 1 is 2. And 2 to the 2 is 4. And 2 to the -1 is a half. And 2 to the -2 is a quarter. And we get this exponential curve that gets closer and closer to 0, but never touches the x-axis. So we have the x-axis is an asymptote to the y equal 2 to the x curve. And this way, there is no asymptote. It keeps going up and up and up and up and up, even for more and more. It goes up really fast. So that's what an exponential curve looks like. 2 to the x. You could do a table for 3 to the x or 5 to the x or anything. Okay? So that's exponential equation, something that looks like this. Now, we were doing compound interest. So we were asking, how long does it take to get to double on that? So let's take a look at how we might have to do something like that. So the compound interest formula is the amount you have after some time. So it's a function of time, or y, years, is the principal, the starting amount, times 1 plus the interest rate. And that could be anything over the number of times it's compounded in the years to the number of times it's compounded in the years times the number of years. We were asking when it doubled. So if and in the example I did, I saying we started with 1,000, so doubling it would be 2,000, and you could divide the 1,000 into the 2,000, and it turns out that this part has to be equal to 2 for it to double the amount you start with to make this. So we're really trying to figure out how to get, when we're trying to figure out how long it takes to double, we're trying to figure out how to make this be 2. Now, if we were doing it daily, we'd be doing one, or let's do monthly. The interest rate, and I used 0.05 in my example, and monthly we divide by 12, and we took it to the 12 times y. So we're trying to figure out y so that this is 2. How do you solve for a power? So that's the question that we're going to be dealing with here shortly. Now, in my compound interest video, we solved by just guessing. We kept trying different numbers until we got it to be close to 2, or to 2,000 with 1,000 in here. So let's talk a little bit about solving for powers. Let's say I had 5 equals something to a power. How do I solve for the something? Well, to get rid of a power, we take it to another power that multiplies to be 1. And we work it out, and we'd get b would equal the 4th root of 5 in this particular problem. Let's do something simpler. What squared is 9? Well, I'd take it to the 1/2 power. Now, you may have said the square root. Well, half power is square root. So 2 times a half gets rid of the 2, and b is the square root of 9, which is 3 or minus 3. That means square root, half power square root. So you can solve for a base by getting rid of the power. Now, what if I had 10 is 5 times something to the 3rd power? To solve this, we divide by the 5. We're trying to get down to what we're trying to solve. So I divide by 5. And I get 2 is something to the 3rd. To get rid of the 3rd, I do 1/3. And so the base has to be the cubed root of 2, or 2 to the 1/3 power. That's how I'd solve for the base there. Okay? So I can solve for the base of the power and its base and its power. What about an equation where I'm trying to solve for the other side? Like f of x equals 3 to the x, or 5 times 3 to the x, let's say that. So what's f of 4? Well, that's pretty simple. We just do type 5 times 3 to the 4th. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 5, which is 405. So in a power equation, if we don't know the base, it's pretty easy to solve for. If we know the base and the number in front and know the power, it's pretty easy to find what it equals on this side. If we don't know this, we can put in all the numbers here and figure that one out. If we don't know the base, we can do what we did here. But what if we had times 3 to some power? What if we have to solve for the power? All right. Now this will go back to kind of what we were doing, what I talked about, and one of the things I said in class on one day was 1/8 times 2 to the x equals 4 to the 3x minus 1. How do we solve for x? Well, we like to go to a common base. 4 is 2 squared. 8 is 2 to the 3rd. These all could be written as powers of 2. 1/8 is 2 to the minus 3. The minus means put the 2 to the 3rd in the denominator. 2 to the 3rd is 8. So that's another name for 1/8 times 2 to the x. So these have like bases. When you multiply with like bases, you add the exponents. So this is 2 to the x minus 3, or minus 3 plus x. We add the powers when we multiply. On the other side, we have 4, which is 2 squared, to the power 3x minus 1. Well, what do you do when you got a base to a power to another power? Well, if we had x to the 2 to the 3rd, that's x squared times x squared times x squared. Cube means multiply this times itself 3 times. So that's x times x times x times x times x. That's x to the 6th, which is what these multiply to be. So when you have a base to a power, you multiply the powers. So 2 times 3x is 6x, and 2 times minus 1 is minus 2. Now they have the same base, and they're supposed to be equal. So the powers must be equal. So x minus 3 must equal 6x minus 2. So if I subtract x from both sides, add 2 to both sides, x equals minus 1/5, dividing both sides by 5. So minus 1/5 will make this side equal to this side if I put minus 1/5 in for the x's. And you could work that out and check it. You could type it into your calculator and check it. So how do I do that problem that I suggested? 2 equals 5 times 3 to the x. This problem, everything was some power of 2. It made it easy to do. These are not some power of a common base. So on your calculator, they have a tables that contains any number to a common base. That base being one of two options. On your calculator, there's the button log. And log of, let's say, 2 tells me the power that I can take 10 to get 2. 2 is 10 to this power. Let me prove that to you. I'm going to take 10 to that answer, and my calculator will say that's a 2. So 2 is 10 to the log of 2. So 5 is 10 to the log 5. Let's prove that stuff. Log 5 is that number. If I take 10 to that number, I get 5. 10 to the log 5 is 5. So this button log is just a bunch of tables for telling us what is the power of 10 that makes 5 or 2 or whatever we need. Well, we need 3. So that would be 10 log 3. That's a 3. And 3 is to the x. Now, how do we solve this? Well, when we got a base to a power to a power, we multiplied. So this is 10 to the x log 3, 10 to the log 5 equals 10 to the log 2. And when you multiply, you add the powers, so we get 10 to the log of 5 plus x log 3 equals 10 to the log of 2. Oh, same base, only one base. So now this must equal this. Now, remember, this is just a number. Log of 2 was something up there. Log of 2 is 0.3. It's just a number that you take 10 to get 2. This is just a number, and this is a number times x. So we have a number equals a number plus x times a number. Now, if I had an equation that said 5 equals 7 plus 2x, a number equals a number plus a number times x, just like I have here, I'd subtract this over, subtract the 7 off the 5, and then divide by 2. I'm going to subtract log 5 from both sides. That number minus this number equals x times this number. And then if I divide by log of 3, I know what x is. Let's figure it out. Log 2 minus log 5, close parenthesis, is this number, divided by log of 3 is that number. That's the x that should make this work out. Let's check it. 5 times 3 to that power, my answer, should be 2. And it works. So the answer to this equation is that. This calculator, and most calculators, have 2 log buttons. This 1 log button here that calculates everything in base 10, and you know it's base 10. It's looking for 10 to what power to make 2 if you type in log 2. It says the opposite of doing log is 10 to the x. If you take 10 to the log 2, you get 2. This is base 10, base 10. There's this log, which is base e. I could have done this whole problem in base e. And again, e is this number over here, second divide. It's 2.718281824. Anyway, I could have done this problem in base e. I could have said 2 is e to the L natural log, that's called natural log of 2. I'll show you. E to the, I'm going to use this e to the something, ln2 will be 2. That's another name for 2. 5 is e to the ln 5. And 3 is e to the ln 3, and that was to the x. And then if we do exactly what we did before, this becomes x ln 3 times e to the ln 5 and when I multiply, I add, so I get e to the ln 5 plus x ln 3 equals e to the ln 2. So this has to equal this. And so I got to move up here. So I have, since the bases are the same and there's a single base on each side, ln 2 equals ln 5 plus x times ln 3. That's just a number, that's just a number, that's just a number. And that's again like the equation we had down there. So it'd be ln 2 minus ln 5, taking ln 5 from both sides, moving that over, then dividing by ln 3, and that will be x. Down here we did log 2 minus log 5 over log 3. Here we're doing natural log 2 minus natural log 5 over natural log 3 to get x. And that comes out to be exactly the same answer. Let's do this one. Natural log 2, close parenthesis, minus natural log 5, close parenthesis. All of that, so I better go back here and put a parenthesis here, insert a parenthesis. All of that divided by ln 3 gives me the same answer as I had for parenthesis log 2, going down here, log 2 minus log 5, that's the numerator, close it, divided by log 3, and I get the wrong answer because I didn't do divide in there. I need to put in insert a divide. I get the same answer as I did with ln's. I get the same answer with log base 10. So it doesn't matter whether I do it in base 10 or base e or any base. So in an exponential, you can solve for the base like I did, or you can solve for the other side. If we know all the stuff on this side, we can do it like I did here. We can solve for base like I did here or like I did here. Or you can solve for the power by making a common base using logs. I'm going to stop there.